Imagine walking into a factory where machines talk to each other, monitor their own health, and predict failures before they occur, saving thousands and preventing unplanned downtime. This is the Industrial Internet of Things, or IIoT, and in this series, I will show you how to build your own smart industrial systems step by step using affordable hardware and open source software. Before we dive in, let's zoom out for a moment. The IIoT is part of a big story, the fourth industrial revolution, which is the same as Industry 4.0. Industry 1.0 started with mechanization using steam power. Industry 2.0 brought electricity and assembly lines. Industry 3.0 introduced automation and PLCs. And now, Industry 4.0, where machines, sensors, and data are all connected to make factories smart. The IIoT takes IoT technology of sensors, data, and the cloud and applies it to industrial environments where there are machines, transmitters, actuators, controllers, and the SCADA system at large. IIoT intelligently monitors processes, optimizes performance, automates complex decisions, predicts failures before they happen, and automatically triggers maintenance. Take, for example, vibration and temperature sensors on a pump, stream data through a gateway for analysis, and trigger maintenance automatically. This is one of the most common IIoT applications, predictive maintenance. To understand how the Industrial Internet of Things systems work, let's break them down into 5 layers. The first is made up of sensors, actuators, PLCs, and instruments that measure temperature, vibration, pressure, and other parameters. Data is reliably exchanged from this layer in real time with other layers using various forms of connectivity. Connectivity is the layer that moves data from devices to the edge or cloud using wired or wireless networks in real time. Common wired protocols include Modbus, Ethernet IP, and Profinet, while wireless options include Wi-Fi, LoRaWAN, 4G, 5G, and Bluetooth. This layer is the backbone of IIoT. At the edge, close to the machines, small computers or gateways like Raspberry Pi, Siemens IoT 2040, or advanced tech devices process data locally using tools like Node-RED, Eclipse Cura, AWS IoT Greengrass, or Azure IoT Edge for timely response. Once the data is processed, it moves to the cloud for storage, analytics, and AI. Here is where big data platforms and machine learning models turn raw numbers into insights. Open source platforms such as ThingsBoard, Fireware, or Eclipse Capua store, visualize, and analyze the data. Commercial platforms to consider are AWS IoT Core, Azure IoT Hub, and Siemens MindSphere. And finally, applications and dashboards, where operators use web dashboards and mobile apps to visualize performance, receive maintenance alerts, work orders, and MES integrations to close the loop. Typical tools are Grafana, Power BI, or built-in dashboards in cloud platforms. Traditional industrial systems used to be closed, expensive, and difficult for students or small businesses to access. But open source software has changed that. Today, anyone, even a student with a laptop, can build a complete Industry 4.0 solution. For example, you can use Node-RED to read Modbus data from your Arduino Nano PLC, send that data over MQTT to ThingsBoard, store it in InfluxDB, visualize it in Grafana, and even integrate AI with Fireware or Capua. IIoT powered by open source software gives you freedom, flexibility, and learning by doing. The benefits of IIoT are massive, but it's not all smooth sailing. They include reduced downtime, improved efficiency, better product quality, enhanced safety, and lower operational costs. The challenges are integrating legacy machines, ensuring cybersecurity and data privacy, managing massive data volumes, and finding skilled engineers to maintain systems. But as open source ecosystems grow and edge computing gets smarter, these challenges are being solved faster than ever. This tiny computer can connect your PLC to the cloud, process industrial data at the edge, and build an entire IIoT gateway. In this episode, I will show you how to set up your Raspberry Pi from scratch, fully headless, and transform it into your first Industry 4.0 edge gateway. In Industrial IoT, the edge gateway sits between factory equipment and the cloud. The gateway collects data from PLCs, filters and processes it locally, runs Node-RED or OPC UA servers, then sends clean MQTT data to platforms like ThingsBoard or Grafana. Without the edge gateway, smart factories don't work. To set up the gateway, you will need a Raspberry Pi 3, 4, or 5, a 16 GB plus micro SD card, power supply, Ethernet cable, or Wi-Fi hotspot, and of course, your laptop or PC. We will do this entire installation headless, meaning no monitor, keyboard, or mouse is required. Now, insert the SD card into the card reader and plug it into your computer. Head to the Raspberry Pi software page to download the Raspberry Pi Imager for Windows, in my case, and run the installation. Select your device, which is the Raspberry Pi 4 for me, and go next. I am going with the 64-bit OS, and I will select the SD-MAS storage device. To customize the setup, I am imputing IIoT-gateway as the host name and my region details. Now, I will use Pi as my username and give a password. I will also set my Wi-Fi SSID and password. Enable SSH with password authentication to configure the Raspberry Pi without a monitor, keyboard, or mouse. I am going to skip the Raspberry Pi Connect, review my selections, and write the OS image to the micro SD card. When the write is complete, remove the SD card from the card reader and insert it into the Raspberry Pi. Power it up and allow it to boot up for about 60 seconds. Open Command Prompt on your computer and enter the command ping IIoT-gateway. This is to confirm the Pi's connectivity to the network. To access the Raspberry Pi from the command prompt, enter SSH, the username, which is Pi in my case, and at the host name, which is IIoT-gateway. Enter yes to continue and impute the password you created earlier for the Pi. And now, we are in the Raspberry Pi terminal. The first thing to do here is to update the Pi with the command sudo apt update. And upgrade it with the command sudo apt upgrade-y. This updates all security patches and system packages. You may have to wait a while for this, depending on your internet connection. To get Node-RED running on your Raspberry Pi, open your browser and enter node-red.org. Go to the documentation, Getting Started, and the Raspberry Pi to display the installation procedure. Copy this command and paste it into the terminal to download and run the installation script. Enter Y to commence the installation process. After the installation is completed, follow the prompt and choose what is best for you or skip. For the Node-RED settings file initialization, hit Enter. Use the arrow key to select any applicable options and hit Enter. For user security, you should select a username and password to log into Node-RED, but I will select no for now. On the Node-RED browser page, scroll down to the Auto Start on Boot section. Copy this command and paste it into the terminal. This will enable Node-RED to run whenever you boot up or reboot the Pi. Then enter node-red-start to get the Node-RED services running. Now head to your browser. Enter into the address bar the server name, which is IIoT-gateway:1880. Your IIoT Edge gateway is now live. If you enabled the security setting, you would have to log in. Real-time motor power monitoring reveals hidden problems early, allowing IIoT systems to predict failures before downtime happens. By tracking voltage, current, power, energy, frequency, and power factor, we can detect early signs of bearing wear, misalignment, overloads, pump cavitation, or electrical faults long before a motor actually fails. This is also true for all other industrial electrical installations and home appliances. Let's create a real industrial scenario for this industrial IoT. Imagine a utility service system with several industrial pumps. In such setup, each pump motor could be monitored by a PZEM-004T energy monitor module. Since the ESP32 is the current top pick, these models could connect to an ESP32 acting as a PLC to handle local logic and visualization. The ESP32 then connects to the Raspberry Pi Edge gateway using Modbus ROTU, where Node-RED processes the data, builds dashboards, and prepares it for analytics and machine learning. But today, we will focus on setting up and hooking up a single energy monitor module to the Node-RED Edge gateway. Hooking up the PZEM-004T module to the ESP32 PLC is easy. Its TX pin is connected to the serial 2 RX pin D16 of the ESP32, the module's RX pin to the ESP32 TX pin D17, the 5V pin to VCC, and GND to GND. This option is suitable when the gateway is installed close to the pump. Otherwise, a TTL to RS485 converter module will be required at both ends to extend the distance. For the local power display, a 20x4 I2C LCD is connected to the ESP32 via the SDA pin on D21 and the SCL pin on D22. At the other end of the PZEM module, the external current transformer is connected to this input. The AC power supply neutral connects here, and the live wire connects here. The AC power supply live to the electrical load to be measured goes through the current transformer and then to the load. We will program the ESP32 with the FLProg version 8.2.1, which can be downloaded from the archive using the link in the description. Now, let's create a new FBD program for the ESP32. Drag the energy monitor block to the program and double-click to open the configuration window. Select Serial 2 to reserve Serial 0 for the Node-RED connection. Enable the reset inputs, the voltage, current, power, energy counter, frequency, and the power factor outputs. Let's now connect terminal blocks to the outputs of the block with their corresponding names. We can now start creating the logic for the local LCD by dragging the display block to another board. Double-click on it, add a display, and select the I2C connection type. Change the display row size to 4, the column to 20, and the I2C address to 27 for me. Set the constant as energy monitor, the row to 1, and enable centering. Invert the EN input of the display block. Duplicate the display block. Change the data type to input, the display row to 2, the colon to 1, and connect a string concatenation block to the input. Increase the concatenation block input to 3. Assign small v column space to the first input and capital V to the third input. Connect the convert string block to the second input of the concatenation block and the input of the convert string block to the voltage terminal. Let's now copy these blocks into another board. Right-click to remove the constant from the convert string block input and connect it to the current terminal. Insert a small I colon space to the first input of the concatenation block, a capital A to the third input, and change the display colon to 11. Repeat these previous steps to create a display for power with a small p and a capital V at the concatenation block input, the display row set to 3 and the colon to 1. For the energy with a small e and kWh, row 3 and column 11 for the display. For the frequency with small f and hz, row 4 and column 1 for the display. And finally, the pf positioned at row 4, column 11 of the display. We are going to connect the ESP32 PLC to the Raspberry Pi Edge gateway using the serial 0 Modbus RTU. From the project tree, expand controller, communication, double-click on Add Modbus and select Slave RTU. Expand the Modbus slave, Interface RTU, UART. Double-click on UART and select serial 0. Change the speed to 115200 and ensure that pin PEDE is set to no. Expand variables, holding registers, and double-click on holding registers to add a Modbus tag for voltage with float data type. Ensure that the first and the second register numbers are sequential and not overlapping for the other tags. Add tags for current, power, energy, frequency, and power factor. Drag all the Modbus tags into a new board and connect them to their corresponding terminal labels. With this, we can compile the program and upload it to the ESP32. You should now see the voltage, current, power, energy, frequency, and power factor on the LCD. Now disconnect the ESP32 from your computer and connect it to the USB port of the Raspberry Pi Edge gateway. Log into Node-RED. For our first flow, we need to install the Modbus nodes from the Manage Palette menu option. Go to the Install tab, search for and install the Node-RED Contrib Modbus nodes. Now search for the Modbus Read and the Modbus Response nodes in the Nodes palette. Drag them into the canvas and connect them as shown. The debug node can also be connected to the Modbus Read node to display the monitored power parameters as debug messages. Double-click on the Modbus Read node. You may name it ESP32 Modbus Read. Since the ESP32 Modbus ID defaulted to 1, the unit ID should be set to 1. The Modbus function to read the PZEM parameters should be FC read holding registers with the starting address of 0. Since the 6 ESP32 Modbus float parameters are 2 bytes each, we should set quantities to 12. Then I will set the pull rate to 2 seconds. We need to add the ESP32 Modbus server from here. Name it ESP32 PLC and select the serial type for Modbus ROTU. Search for and select the right serial port from here. ROTU buffered serial type and the baud rate of 115200 to match that of the ESP32. Make sure that the unit ID is also 1. Then hit Update, Done, and deploy the flow. All things being equal, the Modbus read node should show active, and the power parameters should be updated below the Modbus response node. The debug messages from here should also update the parameters. We will first upgrade the circuit from the last episode to include a relay connected to pin D4 of the ESP32 PLC and to the VCC and GND. The relay NO and COM outputs are connected along the live supply to the load for remote shutdown. In FLProg, add a digital output tag for the relay. Assign it to pin D4 and drag it into a new board above. We will now create a Modbus coil with address 0 and connect it to the relay. Then compile and upload to the ESP32 PLC. In Node-RED, let's first process the Modbus read data of the PZEM-004T energy monitor from the previous video. Connect a function node to the ESP32 Modbus read node. Double-click on it and go to the Setup tab to increase its output to 6, corresponding to the number of PZEM parameters. Copy this code from the GitHub link in the description and paste it here for the data processing. The code has functions to process the raw Modbus energy parameters and output them as the actual 2 decimal place values of voltage, current, power, energy, frequency, and power factor. Notice that the function node now has 6 outputs, which we can connect to the debug node. When this Node-RED flow is deployed, the processed energy outputs of the function can be seen as debug messages. To see these messages, I manually energized the relay to turn on the load since I am yet to create the required flow. We can install and configure a dashboard in Node-RED to display the PZEM energy parameters. Go to the Manage Palette menu option. Search for the Flow Fuse dashboard in the Install tab and install it. Scroll down the Nodes palette to see the different dashboard nodes. Let's now drag in 6 of the gauge nodes and connect them to the output of the function. Double-click on the first gauge node. Select the available group and change the name to gauges. Adjust the size of the gauge to 6 by 3. Select your required type and style. Ensure that you remove S from payloads in the value field if present. Change the range maximum to 450. You may adjust the segment value to suit your purpose, but I will delete all but the first. Under Labeling, change the label to voltage, the unit to volts, and click on Done. I will do the same with the next node for the current parameter, with the maximum range of 0.1. The current label and ampere unit. The same goes for the power, with a maximum range of 10, and the unit of watts. And for the energy, with a maximum range of 10, and a unit of kilowatt-hour. The frequency maximum could be 70 Hz. And finally, the power factor with a maximum range of 1. Now, rearrange the order of the parameters in the Dashboard Layout tab. Note that the range could be adjusted depending on the load and power specifications. To show the trends of each parameters, let's drag in and connect the chart nodes to each gauge node. Double-click on the first chart node. Name it Voltage. Add a new group. Name it Trends and select page 1. Adjust the size to 6 by 3. Set the x-axis limit to 1 minute. The y-axis label to voltage with V in brackets, and change the property series to none. Move on to the next chart node for the current and place it on the same trends group with a similar size of 6 by 3. The x-axis limit should also be 1 minute. The y-axis label to current with A in brackets and the property series to none. Repeat the same steps with the appropriate units in the same trends group for the power, energy, frequency, and power factor. Rearrange the order of the parameters in the Dashboard Layout tab if required and deploy the flow. Open the dashboard from here and observe the energy parameters on the gauges and the trends. Let's go back to the Node-RED flow and add 2 dashboard switches. Also add 2 Modbus write nodes and connect them to the switches. Double-click on the first switch and add a new group for the switches. Select the existing dashboard page and adjust the size to 12 by 1. Label the switch Relay and select an appropriate layout. Also configure the other switch with a label of Reset. Now configure the first Modbus write node as a Modbus function of FC5 with an address of 0 and select the existing ESP32 PLC server. Similarly, configure the second node with the address of 1. Deploy the flow and go to the dashboard. The switches are now available to turn on and off the load and reset the energy counter. We can enable remote monitoring and control of Node-RED dashboard with a smartphone. But first, we must head on to Manage Palette in Node-RED and install Node-RED Contrib Remote. This will make available the remote access, remote notification, and remote question nodes in the Nodes palette. The remote access node provides remote access to Node-RED dashboard from a mobile phone. All you must do in the remote access node is to add a remote config node from here. You should keep most of the settings in the config node, but could change the base URL to point to your dashboard and select the server location closest to you. Click on Connect Remote Red app to display the QR code. Now go to your smartphone app store or Google Play to download the Remote Red app. Select Add Node-RED instance and scan the QR code in Node-RED to connect the app to the Node-RED dashboard. Add the config node and deploy the flow. The remote access node should display serving, and the remote red instance should indicate green. You can now select the instance to load the Node-RED dashboard. With your smartphone, you can remotely control your electrical load with the relay and monitor the power parameter trends and gauges from anywhere in the world. The remote notification node will allow Node-RED to send push notifications to your smartphone, alerting you to abnormal conditions. Select the same config node from the access node. We will set the title and the body of the notification message in a function node. You can use the default notification sound or select any other. Now, let's add the function node and paste this simple script from the GitHub link in the description. Modify the set point to your voltage high alarm or alert threshold. The node should output a message payload with the title, voltage, and the body, high, when the set point is exceeded. Connect the function node to the output of the voltage chart node and to the input of the remote notification node. We will simulate the high voltage notification by connecting an inject node to the input of the function node. The inject node should have a value above the set point in the function. Deploy the flow, then trigger the inject node. You should receive the notification on your smartphone that says voltage high. What if you want to immediately act on the notification? Now, we are talking about the question node. For this, we will replace the simple function script with a more industrial-focused function code, also from the GitHub link in the description. The input validation section of the script filters out invalid data or zero readings when the power is off. It ensures no false undervoltage alarms trigger during downtime. The state management section creates a memory for the node, allowing it to remember previous readings, the last time it sent an alert, and how long the fault has been active. The evaluation and direction code compares the real-time value against your custom thresholds to determine if the situation is warning or critical, and specifically notes if the value is too high or too low. The debounce logic section acts as the noise filter. It forces the system to wait a few seconds to confirm if a fault is real before sending a notification, and prevents alerts caused by temporary electrical spikes. All the parameter data are gathered here, and a live summary of the machine health is displayed under the function node. Finally, the script formats the alert with an editable country-specific timestamp. For example, I have the local code and time zone for Nigeria as EN-NG and Africa/Lagos respectively. Russia will be lowercase ROU-uppercase ROU and Europe/Moscow. And Brazil will be PT-BR and America/Sao Paulo. You should look up the one for your region. The timestamp is then sent along with an alert to either of two outputs, one for warning alert notifications and the other for critical alert notifications. Now, go to the Setup tab and increase the output to 2. Ensure that the notification node is connected to the first output, and connect the question node to the second output. In the question node, select the same config, but this time we will set answer 1 to turn on relay with a value of true, and answer 2 to turn off relay with a value of false. Then connect the output of the question node to the input of the relay switch node and the Modbus write node. A key feature of the function node is to process the alert of the different energy parameters. This is achieved by passing each parameter value through a change node that defines the set point. Add a change node between the voltage chart node and the function node. Double-click on the change node, set the name to voltage, and change the rules to set message meta. Then select JSON from here. Go to the same GitHub page in the description, copy the voltage metadata, and paste it here. You can adjust these parameters for the current or frequency. These are for the alarm noise filter time, and how frequently the warning and critical alert should be sent when the fault is still active. You can get the sample scripts of the other parameters from the GitHub link in the description and edit them to match your requirements. I will now connect 4 inject nodes to the input of the voltage change node to simulate the different alert levels. The first is set to 244 volts high warning alert. The second to 253 volts high critical alert. The third to 207 volts low warning alert. And the fourth to 175 volts low critical alert. Connect a debug node to the output of the function for the alert confirmation. When the flow is deployed, you should see a summary of each parameter status below the function. Repeatedly click on the iWarning Inject node for about 5 seconds to trigger the warning alert. You should see the debug warning alert with the trigger voltage, time, and date of the trigger. You should also get the same message as a notification on your smartphone. The critical alert, high or low, require just one click. The debug message is similar to that of the warning alert. Since the critical output is connected to the question node, the smartphone critical eye notification has an option to turn on or off the relay. You may repeat this simulation test for the low alert, and even simulate the alert for frequency and power factor. When upscaling your factory with IIoT, the Remote Thread app is great to have, and it is free for the initial testing period. Industry 4.0 isn't just dashboards, it is real-time decisions from anywhere in the world. For example, when the mechanical side of a motor or pump starts to fail, maybe due to a dry bearing or load misalignment, the motor must work harder. This is reflected instantly in the electrical signature, indicated mainly by current. Most faults first appear as an increase in electrical current long before visible failure occurs. Preventive maintenance application of machine learning using the PZEM-004T will allow us to detect the moment a failure begins, months before total functional failure occurs. Condition monitoring catches problems early by detecting deviations as small as 5% from the normal operating values. For this purpose, the condition monitoring nodes can be installed from the Manage Palette menu in Node-RED. This installation provides 8 nodes. However, today's focus is on anomaly detection. The anomaly detection node supports 7 methods for time series analysis, but we will consider the CUSUM or cumulative sum. It is designed to detect small persistent shifts in the average of the measured parameter, such as the electrical current. The current might only rise by 2 to 3%, which wouldn't trigger a standard alarm, but the CUSUM node will detect this cumulative trend and trigger an alert. Let's maintain the default drift settings, critical threshold, and warning threshold. The expected target current value may be specified, otherwise the mean value is calculated automatically. Connect a debug node to both outputs of the anomaly detection node, since the first output is classified as normal and the second is for warning or critical anomalies. Change the output properties of the debug node to complete message object. When the flow is deployed, CUSUM waiting and warm-up should be displayed below the node in succession. Then the CUSUM value of 0 is displayed if the expected value is unchanged. Observe that the debug messages show the various CUSUM output properties. The ones to note for now are the payload, which is the same as the current input, its anomaly, which could be true if a fault exists, severity, which could be normal, warning, or critical, and CUSUM pose, accumulated deviation from the target. To simulate current drift, connect an inject node to the anomaly detection node. Enter a number value of 0.07 and redeploy the flow. Click on the inject node once. Observe the change in the value of the CUSUM from 0, which gradually returns to 0 again due to the steady current stream from the energy monitor. When the inject node is clicked repeatedly, the CUSUM value increases until warning and critical are indicated successively. The status of these properties could be observed in the debug message window. We can show these anomaly properties on a dashboard with a text node. I will create a new UI group for preventive maintenance and select the same dashboard. Enter current as the label and the default message payload value. Duplicate the text node. Change the label to Anomaly and the value to is Anomaly. Copy and paste this node. Change the label and value to Severity. And finally, custom and custom pose. Then deploy the flow. These preventive maintenance parameters can be monitored along with other power parameters and additional metrics, depending on the configuration. We are only just scratching the surface of preventive maintenance with machine learning. In the next episodes, we will explore how to configure the PZEM energy monitor and the ESP32 with the OpenPLC editor. Hit like and subscribe so you don't miss it, and let me know your thoughts in the comments. Bye for now.